Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine you're on the edge of our solar system, where sunlight fades into darkness and temperatures drop to levels that would freeze steel in seconds. You're aboard a probe, gliding silently past Saturn's luminous rings, when a glimmer catches your eye, a tiny world glittering like a jewel in the void. It's Enceladus, Saturn's enigmatic moon. But this isn't just a frozen rock. As you watch, something astounding happens. Towering geysers erupt from its south pole, spewing plumes of vapor and ice into space, an invitation, perhaps, from an alien ocean hidden beneath. At this same moment, farther inward toward Jupiter, another icy world spins beneath a brutal radiation belt. Its surface is streaked with mysterious reddish cracks, and beneath it, an ocean more vast than all the Earth's seas may churn in eternal darkness. This is Europa. These two moons, once overlooked, now glorified, have become the twin frontiers in our search for life beyond Earth. Why these two? Why Enceladus and Europa, among the hundreds of moons and thousands of exoplanets we've catalogued? Because both possess a rare combination of conditions that scientists consider essential for life as we know it: liquid water, energy sources, and the necessary chemistry. And unlike Mars, which may harbor fossilized hints of an ancient biosphere, Enceladus and Europa are geologically active today. They aren't time capsules, they're living systems, changing, flowing, venting. That makes them not only fascinating, but urgent targets. Let's start with Enceladus, barely 500 kilometers in diameter, roughly the width of the state of Arizona. It might seem too small to host anything extraordinary, but its size is misleading. When the Cassini spacecraft arrived at Saturn in the early 2000s, it began making close flybys of Enceladus. On one daring pass in 2015, Cassini flew directly through one of those icy geysers. What it found was staggering: salty water laced with molecular hydrogen, carbon dioxide, ammonia, methane, and a suite of complex organic compounds, many of the same ingredients present around hydrothermal vents on Earth's ocean floors. It was the smoking gun. Scientists had long wondered if alien oceans could exist on these icy moons. Now one had just blown its contents into space. But how is this even possible on a world so far from the sun? The secret lies in tidal heating. Enceladus is locked in an orbital resonance with Dione, another of Saturn's moons. This gravitational push and pull constantly flexes Enceladus's interior like a stress ball, generating internal friction. That friction, in turn, creates heat, which keeps a vast subsurface ocean from freezing solid. Think about it. A frozen moon orbiting nearly 1.5 billion kilometers from the sun has an underground ocean, and it's warm enough to have hydrothermal activity on its seafloor. Not only that, but this ocean is venting through cracks in the ice, spraying its contents high above the moon's surface where we can actually sample them. No drilling required. The ingredients for life are not just present, they're accessible. Now shift your imagination to Europa, slightly larger than our moon, orbiting the gas giant Jupiter. It's covered in a shell of ice riddled with ridges, bands, and chaotic terrains, places where the crust has broken, shifted, and refrozen. This isn't just an old dead crust. It's active, mobile, almost like a planetary skin in slow motion. Galileo spacecraft data from the 1990s showed strong evidence for an ocean beneath that ice, and more recently, the Hubble Space Telescope captured hints of water plumes rising from the surface, suggesting that Europa too is leaking its ocean into space. Europa's internal heating works similarly to Enceladus's, only even more intensely. Its orbit is influenced by both Io and Ganymede, causing continuous tidal flexing. As Europa is stretched and compressed by Jupiter's immense gravity, friction generates heat within its core. This process prevents its global ocean, possibly 100 kilometers deep, from freezing entirely. And unlike Earth's oceans, which rest atop solid ground, Europa's is locked beneath tens of kilometers of ice. In this vast, dark ocean, heated from below and sealed from radiation above, life might not just survive, it might thrive. But here's where the story becomes even more compelling. On Earth, life doesn't always need sunlight. In 1977, scientists exploring the Galapagos Rift discovered deep-sea hydrothermal vents that released scorching fluids rich in minerals. Around these vents were colonies of bizarre organisms, tube worms, shrimp, and microbes, that survived entirely without sunlight, relying instead on chemosynthesis. These life forms feed on chemical reactions involving hydrogen sulfide, not photosynthesis. If life can flourish in such alien environments on Earth, what's stopping it from doing the same on Enceladus or Europa? Now scientists are beginning to believe that these icy moons may be better environments for life than even Mars. Mars might have once been warm and wet, but its life-supporting days are likely long behind it. In contrast, the oceans of Enceladus and Europa are geologically young and likely still active. They have the energy, the chemistry, and the time necessary for life to emerge. Not just microbial life, but perhaps something more complex. That's why these moons are at the heart of future exploration. They aren't speculative hopes or theoretical worlds. They are real physical places that we can reach, study, and probe in detail. Already, missions like NASA's Europa Clipper and ESA's JUICE, short for Jupiter Icy Moons Explorer, are poised to investigate Europa's ocean and icy crust in the 2030s. And while no dedicated Enceladus mission has yet launched, proposals like Enceladus Orbilander are gaining momentum. The dream to fly through a plume, collect samples, analyze them on site, and maybe, just maybe, detect biosignatures. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. We're building a place for curiosity, for wonder, for cosmic truth seekers just like you. So as we stand at the brink of the unknown with our probes aimed at frozen moons and our minds lit with questions, we must ask ourselves, what if we're not alone, and we never were? The search for extraterrestrial life has often followed a predictable pattern. Look for Earth-like conditions, temperate climates, oxygen-rich atmospheres, maybe some liquid water on the surface. But Europa and Enceladus have shattered that mold. These frozen moons have redefined what a habitable world can look like. To understand why, we have to dive beneath the ice, not just literally but conceptually, into the alien oceans where the rules we know might not apply. Picture yourself standing on the surface of Europa. The sky is a black void, sprinkled with stars, dominated by the massive disk of Jupiter looming overhead like a god in orbit. Beneath your feet, the ice crackles faintly. Somewhere below, tidal forces are flexing the crust, fracturing it, creating friction. Your suit sensors detect microquakes, minute shifts in pressure, subtle echoes from beneath. And then you feel it. A faint tremor, like something shifting in the dark ocean far below. You're standing above a sea we've never seen with our own eyes. A sea that may have existed for billions of years. Beneath that icy surface, up to 30 kilometers thick in some regions, lies a liquid ocean that could be over 100 kilometers deep. That means Europa could have more than twice as much water as all of Earth's oceans combined. And yet it's completely sealed off from sunlight. In such a place, the only hope for life would be chemical energy, most likely from the ocean floor where the rocky mantle meets salt water, and this is where it gets truly exciting. Based on models, that rocky seafloor may be undergoing serpentinization, a chemical process in which water interacts with certain types of rock to produce heat, hydrogen gas, and other compounds that can feed microbial ecosystems. On Earth, serpentinization zones are teeming with life. Deep beneath the mid-Atlantic ridge, in places like the Lost City hydrothermal field, researchers have found thriving microbial communities in complete darkness, living on the hydrogen and methane bubbling out of alkaline vents. These microbes don't just survive, they multiply, forming entire ecosystems where no sunlight ever reaches. Could Europa's ocean harbor similar vents? Could alien life have emerged perhaps billions of years ago and evolved in isolation beneath kilometers of ice? The clues are tantalizing. Europa's surface is crisscrossed with reddish-brown lines, fractures stained with what scientists believe are salts, and organic materials from the ocean below. These materials may be pushed upward by chaos terrain, regions where the surface appears shattered and rearranged, as though huge icebergs have been stirred from beneath. One theory suggests that these formations are created when pockets of water or slushy brine erupt upward, disrupting the surface and freezing again. If these upwellings carry signs of biology, they might already be on the surface, waiting for a probe or lander to sample them. But how would we know life if we found it? That's a question planetary scientists are still grappling with. Life elsewhere might not look like anything we recognize, but one thing life has in common, at least as we know it, is its tendency to alter its environment. Microbes leave chemical fingerprints, changes in isotopic ratios, concentrations of methane that vary with the seasons, or the presence of certain amino acids. NASA's Europa Clipper mission, launching in the coming years, will carry instruments designed to detect precisely these signs. Spectrometers, radar, and dust analyzers will scan Europa's surface, plumes, and subsurface structures during dozens of flybys. It won't land, but it will get closer than we ever have. Meanwhile, on Enceladus, the case for life is arguably even stronger. That's because Enceladus does more than hint at what's below. It gives us samples. Its plumes erupt with enough force to escape the Moon's weak gravity and form one of Saturn's rings, the E-ring made largely from ice particles ejected by Enceladus. Cassini flew through these plumes multiple times, each pass revealing more complex chemistry. Some molecules, like dihydrogen, hinted at hydrothermal vents at the seafloor, suggesting an energy source akin to Earth's black smokers. But it wasn't just raw elements that were detected. In 2018, scientists announced that they had found complex organic macromolecules, long carbon-based chains, in the plumes. This was the first time such large organic compounds had ever been detected off Earth. And that changed everything. Think about what that means. Enceladus is not just expelling saltwater and heat, it's expelling the molecular building blocks of life. And we're catching them. If Earth's oceans had been this accessible, we might have discovered deep-sea life centuries earlier. Now in the 21st century, we stand on the verge of doing the same with alien oceans. The possibilities are dizzying. Of course, there are skeptics. Some argue that organics alone don't mean life. After all, organic molecules can form abiotically, without biological processes, through things like cosmic radiation or interactions with silicate rocks. But the combination of ingredients on Enceladus makes the skeptic's case harder to maintain. You have liquid water, a source of energy, organic salts, and a chemically rich ocean in direct contact with a rocky core. On Earth, that combination always leads to life. Always. If it hasn't on Enceladus, then why? Is Earth truly special? Or are we just missing something? This debate is more than academic. It strikes at the heart of the Fermi Paradox. If life is easy to make, why haven't we found it yet? Perhaps the answer lies not in distant star systems, but right here in our cosmic backyard. Enceladus and Europa may be the Rosetta Stones of astrobiology. Decoding their secrets could tell us whether life is a cosmic accident or a cosmic imperative. And if we do find signs, actual biosignatures in those plumes or chaos terrains, it would raise even bigger questions. What kind of life? Is it DNA-based like ours, or something altogether different? Could we learn from it, or would it pose risks we don't yet understand? In science fiction, alien oceans are often imagined as realms of wonder and danger, but in reality, they're places we may soon explore, not with starships, but with data, drones, and deep space instruments. We're entering an age when the dream of discovering life beyond Earth is no longer centuries away. It's just one successful mission away. All it takes is one molecule, one measurement, one anomaly in a plume sample. And everything changes. Imagine. It's the year 2030. A spacecraft the size of a van, sleek and glittering with solar panels, glides silently into orbit. Around Europa. This is the Europa Clipper, a robotic emissary from Earth forged in laboratories and fueled by centuries of questions. As it loops around Jupiter's icy moon, the instruments aboard begin to stir. Radar pulses slice through. The crust spectrometers scan the jagged surface, and mass analyzers whisper secrets from the thin air. Somewhere in the silence of deep space, the search for alien life begins in earnest. The Europa Clipper, scheduled for launch in the mid-2020s, represents one of the most ambitious attempts in human history to study an ocean world. Unlike previous orbiters, Clipper won't orbit Europa directly. It will perform dozens of flybys, using Jupiter's gravity to slingshot between orbits. This allows the spacecraft to reduce radiation exposure while sampling Europa from multiple altitudes and angles. Each pass gathers data, high-resolution images, ice-penetrating radar profiles, thermal maps, and, perhaps most crucially, chemical readings from any active plumes it might intersect. But Clipper is only the beginning. At the heart of this new wave of exploration lies a tantalizing possibility. What if we could go deeper, into the ice itself? Enter concept missions like the Europa Lander, a proposed robotic explorer that would descend to the surface and drill into the top layers of ice. Its design includes sterilized tools, robotic arms, and chemical analysis chambers. If plumes do exist and deposit material on the surface, as many scientists believe, then scooping just a few centimeters of ice could potentially reveal biological fingerprints, isotopic ratios, complex organics, chirality patterns in amino acids. These are all biosignatures we could detect. The implications of finding them? Earth-shattering. It would mean we are not alone in the universe, at least not biologically. That life, at its most fundamental level, is not an anomaly of Earth's temperate climate or its stable orbit, but a natural byproduct of the universe wherever conditions permit. But while Europa offers mystery cloaked in ice, Enceladus offers something far more tangible, a trail of breadcrumbs being hurled into space. In 2015, when the Cassini spacecraft flew through Enceladus's plumes, it wasn't a blind maneuver. It was precision choreography. Moving at over 30,000 miles per hour, Cassini swept through the geysers like a hand catching snowflakes, collecting data with instruments designed decades earlier. What it found was astonishing. Not just water vapor, but dihydrogen, carbon dioxide, methane, salts, and even molecular nitrogen. These are not random fragments. They're ingredients selected by geology or biology and cast upward through fissures in the ice. Perhaps the most thrilling development came years later, when a reanalysis of Cassini's data revealed nitrogen and oxygen-bearing organic compounds far more complex than expected. These were macromolecules, long carbon chains with molecular weights of hundreds of atomic mass units. On Earth, such compounds are rarely produced without biology. While abiotic pathways do exist, they require highly specific conditions. This has fueled a new urgency: return to Enceladus. Not just to orbit, but to dive into the geysers again, this time with better tools, sharper instruments, and targeted experiments to answer the question directly. That's where missions like Enceladus, Orbilander come in, a dual-mode spacecraft currently in the design phase. The idea? Orbit Enceladus for hundreds of days, analyzing the plumes, and then descend to the surface for direct sampling. Its lander would touch down near the Tiger Stripes, 4 parallel fractures at the Moon's south pole where plumes erupt most actively. Instruments would scoop up fresh deposits, heat samples to release gases, and scan for biomarkers. Think mass spectrometry, chromatography, laser desorption techniques, all tools designed to peer into the molecular soul of a sample. But challenges abound. How do you avoid contamination? If you bring Earth microbes to an alien ocean, you risk altering the very thing you came to study. That's why planetary protection protocols are so strict. Spacecraft destined for Europa or Enceladus must be built in ultra-clean facilities, sealed, baked, and sterilized to minimize the chance of false positives. And then there's the energy issue. How do you power instruments in deep space where sunlight is a weak trickle? Radioisotope thermoelectric generators, essentially space batteries powered by decaying plutonium, offer one solution. They've powered everything from Voyager to Perseverance, and they may do the same for future ice explorers. Even more radical are the concepts being sketched out in astrobiology labs today. Imagine a cryobot, a robot designed to melt its way through ice using heated elements or lasers. Behind it trails a fiber optic tether, feeding data back to the lander above. Once it reaches the ocean below, it releases a submersible like a miniaturized autonomous drone. Equipped with cameras, lights, chemical sniffers, and perhaps even robotic arms, it explores the alien sea, alone, in darkness, beneath an ice ceiling thicker than the tallest mountain on Earth. Science fiction? Not entirely. NASA's Jet Propulsion Laboratory and the European Space Agency have both prototyped cryobots for Antarctic expeditions, using them as analogues for Europa and Enceladus. In 2019, one such probe drilled into a frozen lake beneath Antarctica, deploying a drone that swam beneath the ice. If we can do that on Earth, we can eventually do it in space. It's just a question of engineering, funding, and time. Yet amid all this optimism lies a deeper, more philosophical question. Even if we find life, what then? Would we celebrate it as a triumph of human curiosity, or quarantine it in fear of contamination? Would we seek to communicate, even if it's just with microbes, or would we leave them alone as sacred artifacts of a universe beyond our own understanding? These aren't just scientific questions, they're ethical ones. They touch on how we see ourselves in the cosmos, because in the end the question isn't just, is there life on Europa or Enceladus? The question is, are we ready for the answer? As we venture deeper into the unknown, a new reality begins to take shape. This search for life is not merely an intellectual pursuit, it's a quest for understanding who we are as a species. Are we truly unique in the cosmos? Are we a solitary spark of consciousness in an endless dark ocean of stars? Or are we part of something larger, something far more intricate and complex than we ever imagined? It's not just about Europa and Enceladus either. These moons are part of a broader revolution in our thinking, a revolution spurred by breakthroughs in both our technology and our philosophy. Just a few decades ago, scientists were still grappling with the very notion that life could exist beyond Earth. The prevailing belief was that life was an Earth-centric phenomenon, shaped by conditions here, and thus any search for extraterrestrial life would be pointless unless we could find similar conditions. Now, thanks to advances in molecular biology, biochemistry, and planetary science, the scope of our search has dramatically expanded. Life, it seems, can adapt to a variety of environments, some of which were once thought to be completely inhospitable. For example, microbes have been discovered thriving in boiling hot springs, acidic lakes, and the frigid depths of our oceans. These extremophiles, organisms that live in extreme conditions, have given us a new lens through which to view the universe. If life can exist in the harshest conditions on Earth, why not in the dark depths of Europa's ocean or Enceladus's hidden water world? But here's the thing. While the potential for life on these moons is exciting, it also brings us face to face with one of the greatest paradoxes in astrobiology, the Fermi Paradox. If there are so many habitable worlds in the universe, and life can thrive in such a wide range of environments, why haven't we found evidence of extraterrestrial civilizations? The paradox isn't just a matter of distance or technological limitations, it's about the unknowns, the vastness, and the timescales involved. The universe is over 13 billion years old. Civilizations could have risen and fallen long before Earth was even formed. So, even if there are other life forms out there, how do we find them? How do we detect their presence? The search for life on Europa and Enceladus provides one answer to this question. It's not just about finding intelligent life or civilizations. It's about discovering the building blocks of life itself. Understanding how life can arise, evolve, and survive in places completely alien to us is the key to solving the larger puzzle. And that's where these icy moons come in. Europa's subsurface ocean is thought to be in contact with the moon's rocky mantle, a prime condition for chemical reactions that could give rise to life. The heat generated by tidal forces from Jupiter's immense gravitational pull could create hydrothermal vents on the ocean floor, similar to those found on Earth. These vents, which support thriving ecosystems deep beneath the ocean, could be the key to unlocking the mysteries of Europa's potential habitability. Enceladus, too, presents a tantalizing possibility, Beneath its icy shell lies a global ocean. Cassini's flybys confirmed that the Moon has active geysers that spew water vapor, salts, and organic compounds into space. The fact that these geysers exist at all suggests that there is some form of geothermal activity beneath the surface, perhaps a sign of life-sustaining processes. If life can exist in these oceans, it would offer a glimpse into the resilience of life itself, suggesting that life could take root in environments far more extreme than anything we can imagine. As we look at these moons, we see not just the potential for life, but the potential for an entirely new understanding of what life is and how it operates. These worlds, seemingly frozen in time, might hold the key to answering the most profound question humanity has ever asked. Are we alone? Yet, even as we begin to peer deeper into these distant worlds, we are confronted with the limits of our knowledge. The truth is, we don't know exactly what we're looking for. The forms of life on Europa or Enceladus may be radically different from anything we've seen on Earth. Perhaps, instead of simple microbial life, we might discover entirely new biochemistries, life that exists without the need for oxygen or that metabolizes in ways we can't yet comprehend. This uncertainty is both humbling and exhilarating. The search for life on these moons is not just about uncovering evidence of alien organisms. It's about expanding our understanding of life itself. Each new discovery, whether it's the detection of organic molecules or the identification of hydrothermal systems beneath the ice, brings us closer to answering one of the greatest existential questions humanity has ever asked. Are we truly alone, or are we simply one thread in a vast, intricate web of life that stretches across the cosmos? This quest has the potential to change the way we see ourselves. It challenges us to rethink our place in the universe and reimagine the limits of possibility. It raises questions about what life is, what it means to be alive, and how we might one day coexist with other life forms, perhaps in ways we can't yet fathom. And so, as we prepare for the missions that will take us to Europa, Enceladus, and beyond, we are not just sending robots and instruments to explore distant moons. We are sending our curiosity, our drive, and our hope that one day we will discover something, anything, that confirms that we are not alone in the universe. These missions represent humanity's greatest quest for knowledge, a search for the unknown that will continue to shape the future of space exploration for generations to come. But there's another question we must consider as we peer into the depths of Europa's oceans or the geysers of Enceladus. What will we do once we find life? How will we respond to the discovery that we are not the only sentient beings in the universe? Will we see these newfound life forms as peers, fellow travelers on this cosmic journey, or as something alien and foreign to be studied, protected, or even feared? As we prepare to launch new missions, there's one thing we know for certain. This search is about more than just finding life. It's about understanding ourselves in the grand cosmic tapestry, a search for our place in the universe. The search for extraterrestrial life is not just about science. It's about the very essence of what it means to be human. The more we learn about the possibility of life beyond our planet, the more we confront our own limitations, fears, and hopes. We're standing on the precipice of something truly remarkable, a moment in history that could forever alter our understanding of life, the universe, and our place within it. Europa and Enceladus are not just two of the most fascinating moons in our solar system. They represent the frontier of a profound journey into the unknown, a journey that will define the future of humanity. It's hard to grasp how much this could change everything. Imagine, just for a moment, that one of these missions uncovers definitive proof of life on Europa or Enceladus. The implications would be staggering. This wouldn't be a minor scientific discovery. It would be an intellectual and philosophical revolution. It would shake the very foundations of everything we thought we knew about biology, evolution, and the limits of life itself. Suddenly, the search for life would no longer be a question of if, it would be a question of how and where. The possibility of life beyond Earth would be real, it would be tangible, and the ripple effects would be felt across every aspect of our society. From a scientific standpoint, the discovery of life beyond Earth would open up an entirely new field of study. Astrobiology would become a central pillar of modern science. We would have to rethink everything, from the basic building blocks of life to the potential for complex ecosystems on distant worlds. Europa and Enceladus, with their vast subsurface, oceans would suddenly become the most valuable laboratories in the universe. Their frozen surfaces would hide countless secrets, and the potential for new discoveries, new life forms, new chemical processes, new ways of thinking about existence would be limitless. But the discovery would also have profound cultural and philosophical ramifications. For millennia, humans have looked to the stars, asking the same question. Are we alone? That question would no longer be speculative. It would be a question with an answer. And that answer would challenge everything we thought we knew about our uniqueness. If life can exist on moons like Europa and Enceladus, then what else is out there? How many more places in the universe are home to life? Perhaps even civilizations far more advanced than our own. This realization could inspire a new era of exploration. No longer would we be a species confined to our small blue planet. We would become explorers, journeying beyond our solar system, to the stars themselves. We could forge a new relationship with the cosmos, not just as passive observers, but as active participants in the great story of life. Europa and Enceladus would be the first steps in this journey, but they would not be the last. And yet, even as we dream of these discoveries, we must also grapple with the risks and responsibilities that come with this newfound knowledge. If we do discover life on these moons, what then? How will we ensure that we don't repeat the mistakes of our own history when we encountered new lands and new peoples, only to exploit them for our own gain? How will we treat this new form of life, whether microbial or more complex, once we uncover it? The ethical considerations will be immense. Just as we protect endangered species on Earth, we must ensure that we do not disturb or harm the delicate ecosystems we may find on Europa or Enceladus. Moreover, the very act of discovery will raise questions about our place in the universe. If we are not alone, how do we redefine our relationship with the cosmos? How do we reconcile the possibility of other life forms with the theological and philosophical questions that have shaped our societies for centuries? The discovery of extraterrestrial life, particularly life that evolved independently of us, could force us to reconsider everything we know about creation, existence, and our role in the universe. Yet, as daunting as these questions may be, they are the questions that drive humanity forward. The pursuit of knowledge is at the heart of what makes us human. It's what has driven us to explore the world's oceans, to sail into the unknown, to look to the stars and wonder what's out there. The search for life on Europa and Enceladus is no different. It's about pushing the boundaries of human understanding, about asking the big questions and, with every discovery, coming closer to the answers. As we look to the future, there are more missions on the horizon, missions that will take us even farther into the reaches of our solar system and beyond. Europa Clipper, set to launch in the near future, will study Europa in unprecedented detail. It will examine the moon's ice shell, its ocean, and its potential for supporting life. The James Webb Space Telescope, too, will offer us new insights into distant exoplanets, examining their atmospheres for signs of life. Together, these missions will help us understand not just the potential for life on other worlds, but the nature of life itself. But no matter what discoveries lie ahead, one thing is certain: the search for extraterrestrial life will continue to inspire humanity for generations to come. Europa and Enceladus may hold the key to unlocking the secrets of the cosmos, but the true discovery is the journey itself, the relentless pursuit of knowledge, the unyielding curiosity that defines us as a species. In our search for life beyond Earth, we are not just searching for aliens, we are searching for ourselves. As you sit and contemplate the vastness of space, the next time you hear about a mission to Europa or Enceladus, remember that you are witnessing the dawn of a new era, an era in which we might finally answer the greatest question of all: are we alone? And if we are not, what does that mean for the future of humanity? The adventure has just begun. The stars are calling, and we are ready to listen. This journey we are on is as much about understanding the universe as it is about understanding ourselves. So, what will we find in the ice-covered oceans of Europa and Enceladus? Perhaps the answer will redefine life as we know it. But one thing is certain: the universe is far more mysterious and far more beautiful than we ever imagined. If you're as fascinated by the wonders of the universe as we are, join us in exploring these cosmic mysteries. Hit subscribe to be part of this incredible journey.